In this lesson, we'll be wrapping up our thermochemistry unit by talking about entropy and Gibbs free energy, the two ideas that let us predict where the reaction will actually happen. The picture on the side illustrates a real-life example of the interplay between entropy and energy, in that systems will naturally move toward greater disorder unless energy is put in to maintain that order. That's the idea behind entropy. Nature prefers disorder because there are statistically more ways for particles to be arranged randomly than there are for them to be arranged neatly. We already know that water will spontaneously evaporate at room temperature, even though evaporation is endothermic, as we can see from this reaction energy diagram. It has a positive heat of vaporization of plus 40.7 kilojoules per mole. So the question is, what's providing the uphill push if heat has to be added, if you're below the boiling point of water? This is where entropy steps in. Spontaneous processes aren't determined by enthalpy alone. As you can see, entropy gives us the additional driving force that favors certain reactions even when delta H is positive. Entropy, the symbol is S, is a measure of the disorder or randomness of the particles in a system. Evaporation increases the randomness of water molecules. Liquid becomes gas, so entropy increases. Gases have a much larger entropy than liquids or solids because their particles move freely and can occupy more possible positions. If the entropy of the products is greater than the entropy of the reactants, then delta S is positive. So I have two examples here. We have chlorine monofluoride reacting with fluorine gas to form chlorine trifluoride. So we want to figure out if we have a positive delta S, that is, that you have a delta S value that's bigger than 0, or a negative delta S, where you have a delta S that is less than 0. And so we can see we're going from a mixture, high degree of randomness, to a pure substance. So therefore, we're going to have a negative delta S for this. The material or the system is becoming more organized, less entropic. In the next example, we have pure methanol in the liquid state, and then afterwards we have mixed it in some water, because remember that's what the AQ state means. So we're going from a pure substance to a mixture, so that tells us that delta S is going to be positive in this case. So we have some more examples. So we have the sublimation of dry ice, solid carbon dioxide, going to carbon dioxide gas. We're forming a gas, so that means it's going to be a large positive value. Next one, we have the synthesis of calcium carbonate from calcium oxide and carbon dioxide gas. We are consuming a gas and making a solid. So that means we're going to have a negative delta S. Next one, we have hydrogen monochloride or hydrogen chloride and NH3, which is ammonia, going to form solid ammonium chloride. Because we're consuming gases, just like in example B, that means we're going to have a negative delta S. And then we have this example. We have a mixture of gases going to form just a pure substance, so we're going to have a negative delta S. Another way to look at it is we're starting out with a total of 3 moles of gas. Just imagine the coefficients are a full mole of everything. And we're going to form 2 moles of gas. So whenever you reduce the amount of gas that you have, you're also going to have a negative delta S. So now a key question. If delta S is positive, does that mean that the reaction must be spontaneous? Hopefully you already know that when you start boiling water that it is not decomposing down into hydrogen and oxygen gas. If that were the case, trying to cook on the stove would be rather exciting. You'd have all the hydrogen gas catching on fire and blowing up. So in this case, we have a very large and positive delta S, but we also have a very large and positive delta H. So the thing that allows us to combine both the enthalpy of the reaction and the entropy of the reaction is Gibbs free energy. So another delta. It's called delta G. It allows us to predict the spontaneity of a reaction using the other two deltas. So the equation for it is delta G is equal to delta H minus temperature, capital T, times delta S. Your temperature must be in Kelvin. So if you end up with a negative delta G, that means you have a spontaneous reaction. It's one that actually happens. If you end up with a positive delta G, that tells you it's actually the reverse reaction that is spontaneous. And the way it's written, it won't happen. So looking at an example, let's look at how non-spontaneous the decomposition of water into hydrogen and oxygen is at room temperature. So the temperature at which it evaporates, water evaporates. So we're going to use Hess's law. So it's going to be heat of formation of the products minus heat of formation of the reactants. We look up the values. Remember the heats of formation for elements in their standard states, and both of those are in their standard states, is 0. So that's where these zeros come from. So we have 0 minus 2 times the heat of formation of liquid water. When you do these problems, make sure you are using the value for liquid water, because we also have values for gaseous water or even solid water. So make sure you're using the right value. And we end up with the enthalpy change for this process being 571.66 kilojoules per mole. So yes, a very large positive value for the heat of reaction. Now we can do the same thing with the entropy values. These are also tabulated. And so it's going to be, you add up all of the entropy values for the products and subtract off all the entropy values of the reactants. The difference here is that the entropy of the elements is not going to be equal to 0. So you need to make sure you actually look these up. And the other problem is that entropy values are actually much smaller than enthalpy values. So we're going to end up with numbers that are in terms of joules per mole Kelvin. This is what the unit is, but the key thing there is that we have joules. So before we can actually combine the entropy and the enthalpy in Gibbs free energy equation, we have to make sure we convert our joules into kilojoules. So we go ahead and we say, all right, well, our entropy change for this reaction is 326.34 joules per mole Kelvin. Divide by 1,000, and we'll have that many kilojoules per mole Kelvin, 0.326 kilojoules per mole. Plug it into the reaction, into Gibbs free energy equation. Remember, temperature has to be in Kelvin, and we get that the Gibbs free energy change, delta G for this reaction, is positive 474 kilojoules per mole. So yes, it's very non-spontaneous. Now, if we wanted to, we could figure out what the minimum temperature would be in order to make this reaction spontaneous. The way you do that is you say, well, I have a positive value right now. I want to end up with a negative value. So the minimum temperature is going to be the one at which the signs change. So you want to find where we have a delta G value equal to 0. So we already have our enthalpy and our entropy values. So we're going to set delta G equal to 0. And now we're going to solve for the temperature. And so the temperature ends up being greater than 1400 degrees Celsius, which is far hotter than anything that we would actually encounter in everyday life. Just sort of an interesting aside, one of the things that they were experimenting with during World War II, I believe, is they would heat metal up to really, really high temperatures above this temperature and then drop it into water. And they discovered that it would generate enough hydrogen, and there was still enough heat present, that the hydrogen would then react with the oxygen and you'd have an explosion. So they were dropping molten metal into water in order to make bombs. Just what you need to know. All right, so our wrap up for the entire thermochemistry unit. Specific heat is how much heat a substance must absorb in order to change its temperature. Remember, heat and temperature are two totally different things. Calorimetry is a technique where you can measure the amount of heat that is transferred between substances that are at different temperatures. Enthalpy, delta H, is the heat change in a substance at constant pressure. We looked at two different types of enthalpy changes. If you have a negative delta H, or you have heat being given off, the temperature is going up by itself, not because you're heating it, that would be an exothermic reaction, whereas endothermic reactions would be the reverse. You have to add heat in order to get the process or the reaction to happen. You have a positive delta H. Hess's law allows you to use heats of formation values, or you can combine other heats of reaction values to find the overall delta H for a reaction. And this is because enthalpy is a state function, it's path independent, and also because energy is conserved. We saw earlier on that heating and cooling curves, that whenever you have a phase change, it's because you're going to have a temperature plateau, so we're going to have to use the enthalpy of that particular, associated with that particular phase change, rather than the Q equals mCp delta T, because we don't have a delta T. And then the big idea for this unit is that energy changes tell us how and why chemical processes will happen. So thanks for listening, and I look forward to seeing you in the next unit.